energy constraint and its application to associativity relations on S1 and S3. So please.
Thank you. Thank you for attending this workshop. So today, I talk about estimation of group action and its application to uncertainty relation. So this is the content. And firstly, I would like to summarize the formulation of quantum state estimation. As you know, in the state estimation, we assume that some family of quantum state is a density matrix on the Hilbert space, and we have some estimator. Estimator is described by the pair of P of M. This is measurement, and this is a map of this one. So this one is characterized in this way. This is unknown parameter, but reflecting this parameter, we can generate a quantum state rho theta. Then we apply measurement. Application measurement, we obtain data I, and from I we have some function. Then we obtain estimate. However, it is not so easy to consider that problem in the generic situation. So we consider a very specific case in this talk. This is Hilbert space, and this is group. And we have a H is a subgroup, and we have a quotient space. This one is sometimes called homogeneous space. So our parameter is given as an element of a homogeneous space. And also we consider projective unitary representation of group G, and we assume that this set satisfies the following condition. So this is rho theta, and we apply this unitary FG and FG dagger, and then the parameter is shifted by action to the theta, because theta is the element on the quotient space. So we have an action on the group action on the theta. So in that situation, there is a formulation of the group covariant measurement. So in that case, this part is same as previous, and we have a P of M. P of M is a measurement. Measurement is somehow depending on the subset on the outcome. We have some positive operator. That positive operator needs to satisfy this condition. This is a covariant condition. So B is a set of outcomes. So then, depending on set of outcome, we have some positive operator. That positive operator has this group symmetry. And we consider set of P of M taking values of theta. And this one is a subset. Subset means this subset composed of the covariant measure, covariant P of M. Takes values in theta. So in this case, if the theta is this measurement is described by satisfy the covariant condition, then there exists a positive operator T such that that B MTB is defined by this. So by using the positive operator T, that P of M is measurement is described by in this way. This is the famous result. So now we consider the evaluation error. So in that case, we have an error function, and we have this one. So this is some measure. So depending on the data, we have an integral of outcome. So then this one gives some probability distribution. This is the formulation of quantum information. We have this distribution, and under this distribution, we take average about this error function. So we focus on this average error. However, this average error depends on the true parameter theta. So, sorry. So this is theta is true parameter, and theta hat is outcome. So the difference can be considered error. So then we have this error function. So the Bayesian error is defined by in that way. So this error depending on the true parameter theta. Then we need to take average with respect to the unknown parameter theta. This in that situation, we assume that the prior distribution data. So depending on data, we take this average. So then we all focus on this function, this quantity. So we want to minimize this quantity in the Bayesian setting. And also we often consider minimax setting. Minimax setting consider the following. So we consider worst case of this error. So we have this one. Always this quantity is larger than this one. Now we assume this group covariant condition. So this is a condition for symmetric condition for the error function. Under this condition, we have this result. If error function satisfies this condition and also our estimator satisfies covariant condition, then these three quantities become same. So if these two conditions satisfy, this error function does not depend on data. So in that case, minimax error and Bayesian error become same. So in that case, it is enough to consider only one point due to this covariant condition. So then there is a Kuntstein theorem. This is very famous result. We need to assume this symmetric condition. Under this symmetric condition, we have this equality. So usually we want to minimize the minimax worst case error, minimax error under the all measurement, but it is enough to consider only the covariant measurement. So this one is minimization on the Bayesian setting, and also how to say this one is setting for the minimax setting. But the optimal solution is always obtained by covariant measurement. But in that case, we need to assume theta is compact, and also this Bayesian player needs to be uniform, invariant with respect to the group action. That kind of probability measure exists when theta is compact. However, theta is not compact. In that case, we cannot consider Bayesian situation, but we can consider minimax case. If we consider minimax case, still we have this equality. Then it is enough to focus on the covariant measure. So in this, so for example, Professor Odawa worked on this topic, maybe his PhD thesis, very old result. So then we consider slightly different case because previously we consider state estimation, but now we want to consider estimation of group action. Now we have a project unitary representation F, and we have an input state, and we want to estimate what unitary applied in this box. So this is our problem. So in that case, of course, we need to choose one input state, and we need to make measurement, and we have an estimated G hat. So in that case, our choice can be described as a pair of rho and m measurement. So we need to optimize choice. So in that case, for example, group is given as this one. This how to say, maybe U1. So unit circle. Unit circle. So in that case, our unit are described by somehow in this way. So in that situation, our parameter, our estimate is an element of the group. So in that case, we have a error function in this way, and we assume some symmetric condition. So then we need to impose this condition. So this is some symmetric condition for the error function, and we take average. So in this case, our average error is described by this one. So this one depends on unknown parameter group G, and E is a pair of our choice. So similarly, we can define Bayesian case and also a minimax case in the same way based on this one. This is our problem. So we want to find a best choice, and we want to know behavior of this minimum error. So then we have an extension of quantum Stein theory in the case of group action. So we have this is minimax error. So minimax error we want to minimize by choosing the rho and n. But this one is simplified in this way. It is enough to consider mu is a uniform measure when G is compact, and if and rho is reduced to the distance to pure. We have this restriction, and measurement should be covariant. So it is enough to consider very simple case. So we don't need to consider generic measurement or generic state. And even in the G is not compact, we have a similar one under the minimax criteria. So now in order to resolve that minimization problem, we want to introduce the concept of Fourier transform. As you know, Fourier transform is defined on the vector space R usually, but that kind of concept can be extended on the generic group G on the irreduced unitary representation. This is somehow slightly advanced concept. So firstly, G hat is a set of irreduced unitary representation space of G. So then we define L2G hat. L2G hat is that is some product or with respect to G hat, and we define L2V lambda. V lambda is irreduced space, Hilbert space, irreduced representation space V lambda. Lambda describes an element of G hat, and we consider Hilbert-Schmidt operators. So this one is the space of the Hilbert-Schmidt operator on the irreduced space. So then we take that kind of direct sum, and we consider Fourier transform in this way. So this is the generalization of usual Fourier transform. So what is this? Phi is so phi L2 yes. Phi is the element of L2G. So phi is a function defined on element G. So depends on G, we have a phi G. This is only a complex number. No. This is a matrix. L2 phi. Sorry. This is only complex number. Phi G is only complex number, but F lambda is a matrix because this is irreducible representation on the this irreducible space. So this is representation. This is unitary matrix, unitary operator, and this is complex number. And we take average with respect to the uniform Hall measure with respect to element group G, and we take lambda. So this one is lambda because this one is a direct sum. So then, in order to define the image of this one, we need to identify each matrix on the each irreduced space. So this one describes the matrix on the this irreduced space lambda. So we define this one for each lambda. This is a Fourier transform, but we have an inverse map of this one. Inverse one is defined by this one. So of course, the product of both become identity. So inverse is this is the element of a lambda. A is this element, and a lambda is Hilbert-Schmidt operator on the V lambda irreduced space. And for each irreduced space, we take this trace with this unitary representation. So then we take this D lambda. D lambda is the dimension of the V lambda, and this one, and we take summation for all irreduced representation. Then we have this one. This is the inverse. So we need to explain the relationship between the input system and inverse Fourier transform. Because now please remember that our problem is this one. So our problem is this one. We need to estimate this one, but we only have in the physical system, we only have a representation on the hidden space H. So we need to consider generic situation. But that situation can be converted to the some inverse of Fourier transform because our Hilbert space can be described by in this way. So V lambda is Hilbert space, and we can decompose in that way. And in general, any Fourier any representation space can be written back in this way. This is multiplicity. This is multiplicity. So once we have some irreducible, once we have a unitary representation, we have sometimes we have the same equivalent component, equivalent representation. Representation exists in the given representation, but in that case, we need to consider multiplicity. So then we have this kind of unique description. So in this sense, for any pure state on this vector space, we can describe by in this way. So V lambda is element of this one. V lambda and tensor Cn lambda. So phi lambda can be considered as an element of this one because phi lambda is originally this element, but we choose suitable partial isometry from V lambda to this multiplicity space. By fixing this partial isometry, we can consider that this element is element of this one. So in this sense, this element input state can be considered an element of this one in this way. Of course, this isometry is dependent on the choice of phi, but depending on phi, we can consider this element is can be considered element of L to G hat. So in this way, for the input state, we can define inverse Fourier transform in this way. So we have a result. Previously, we needed to consider this minimization, but this minimization can be considered as an optimization rho and n. But now we have a rho and BR state. If we focus on the some suitable covariant measurement, in that case, this error equal to this error. This error. Of course, that kind of partial isometry corresponds to the choice of measurement. But using that simple correspondence, this error function equal to this one. This is inverse Fourier transform. So X is some element now, but element is the pure state. Element is corresponds to that pure state. X corresponds to pure state. And we have an inverse Fourier transform. Then we have a distribution. With respect to this distribution, we can take average on the error function. Then we have this quantity. But this quantity is same as this one. So then essentially the minimization problem reduces to this minimization. So essentially this one corresponds to the choice of input element. This element. So, but sometimes sometimes there is no multiplicity. Sometimes, so in that case, some element of G hat does not appear in Hilbert space H. So then, in this sense, we need to consider this support. So under this support, we need to consider this minimization. So that kind of input X is depend on the support of Hilbert space. So now I want to consider that example. So most simple case is G equal to R. In that case, how to say dual space. Dual space is a unitary representation. So corresponding to the dual space corresponds to the unitary representation. Then that one is also G hat equal to R. And we have a same measure on this way, and we have this input space. And the distribution of this one, if phi is the input quantum state on this R, L to R, so then we have this distribution. Then we have a compact, yes, this one. But sometimes if we allow any file, so our estimate is very nice. In that case, we need some restriction. Otherwise, the problem is somehow trivial. So sometimes we make a support constant, support constraint. So under this constraint, we need to minimize this one. That minimum is given as this under this support constraint. So this input state is optimal in that situation. Next, we want to consider G equal U1. In that case, G equal U1 case, G hat is G integers. So in this case, input state can be considered as element L2 G, Z, and we have this condition, normalization condition. Then the distribution of our estimate is given this one. Then average error is minimization of average error is this one is given to this one. Then of course, if we allow any file, so our estimate become precise as you like. But we need some limitation. For example, the support of G is limited to the minus G and G. So under this condition, our optimal solution is this one, and the minimum is attained by this one. This is no result. So, but our setting can be extended to the projective unitary representation. In the case of projective unitary representation, we need to fix one factor system. Factor system means that G, FG, and FG prime, and FGG prime inverse. This one must be one in the case of conventional unitary representation. But in the case of projective case, this one becomes some complex number constant. So that complex number constant must be fixed. So one projective representation gives this one, but another projective unitary representation gives a different this constant. So sometimes you cannot consider a combination of or superposition of such a kind of different factor system projective representation. That's why it's impossible. So then we need to fix one factor system, this one. So once one fixes this factor system, we can define set of irreducible projective representation. So this one somehow depending on the factor system. So depending on the factor system, we can similarly define inverse of Fourier transform, and we can define this one, and we have a same characterization. We need this characterization. So now we consider a case of compact group. So in the case of compact group, this kind of error function displayed by using these characters. So using this character, we can consider this one. But for example, if error function displayed in that case, the minimum error is displayed by in this way. So this one is called Richard constant. This is somehow complicated, but this constant explains some relationship between the several irreduced components. This is one result. So in the case of group SO3, so in that case we often consider this gate fidelity. So under this gate fidelity, this Richardson constant is this one, and if the irreduced representation is this one, this is lambda is somehow minimum spin. So in this case, our optimization can be solved in this way, and we have this one. So in this case, this one behave of inverse of m square. This is characteristic. So, but in the case of SO3, people often consider projective representation. In the case of projective representation, that kind of support is this one, the half integer. We have only half integer. In that case, we have a similar characterization, and we have this one. And in the case of SU2, we have a slightly different error function, this one. Then we have a similar characterization in this way. So now I want to stop the first part. Maybe this is for 20 minutes. No?
Yes, I think so, yes.
25.
Maybe a good timing to ask if there are questions about the model. So I have one question. Are you considering one-shot estimation? So you have only one copy of row, or you consider more than one copy? Only one, I think, right?
Yes, in that situation, we have a very big representation. Then currently, yes, this problem is one element row.
Okay.
Of course, but in some sense, how can we realize this one? Sometimes this one is realized by the n-tensor product of some given representation. So in this sense, this setting includes some n-copy setting. But in that case, the input state allowed to use entangled state, entangled across the many copies in this setting.
Okay, thank you. And I have another question. So all the examples you described use the infinite groups. So is the problem interesting if you consider finite groups? Or is it not interesting?
This is infinite. Of course, the group is infinite. Compact, but infinite.
Yes, but for the case of finite groups.
Of course, finite group is included, but I don't. Today I don't prepare the finite group.
So the problem can be considered also over finite groups, but in today's you consider infinite groups. Okay, thank you.
Yes, this general formula is holds even in the finite group.
Yeah.
Yes, this formula holds even in finite group.
Okay, thank you. Is there any other questions or about the model or more general questions? Okay, then maybe we can proceed to the second part of the talk.
So then on the next part, we consider energy constraint on that problem. So our error is described in this way. So then we want to impose energy constraint. Energy constraint means that, for example, energy constraint for the input state. H is Hamiltonian. So we impose the input state should be smaller than E. So previously, we imposed some condition for the support of input state. So what is this? I can't remember. Yes, this is support. So previously we restrict support of input state, but sometimes we have some infinite dimension space, but we have another restriction, for example, energy constraint. We discussed that setting. So in this case, we impose an energy constraint. Under this energy constraint, we have this inequality. So then this is energy constraint. This is inequality energy constraint. Then we under this condition we minimize this one. This is the next problem. For example, very simple case, group equal is R and G hat. In that case, we consider energy is Q square multiplication operator. Now we consider system is L to R. So then we import this energy constraint and we minimize this quantity. And that problem can be converted to this one and converted to this one. As you know, this is a very simple problem. This is the Robertson uncertainty relation. So then we have this minimum value, and the minimum is attained by this Gaussian input state. This is very famous result. But now in the next step, we want to consider more generic group, compact groups. So in that case, we need to consider massive function. So we employ massive function. This is very useful too. So in the to define massive function, we consider this periodic differential operator. So then we have this minimal function, and we have this eigenfunction, and these eigenfunction on the space on this one. So this is even function. This is odd function, and this is even odd. And also this is periodic, and this is maybe anti-periodic. So in this, we have four function, four minimum function. So this is important to next part. Finally, we consider estimation of a group element of U1. So in this case, we have this one and this one, and energy. Now we consider Hamiltonian this one, k square. So square, not the number operator. We consider square is how to say energy. So in that case, we minimize this one. This is the error function, and this problem can be converted to this one. But considering the this problem, the optimal solution is solved by this one. And so this is and all this one. That's a minimum eigenvalue A0 in the previous one. So this one is asymptotically behave in this way. Energy is very large. We have this 1 over E, and energy is very small. So this one is 1 minus very small this one. So that in that case, optimal input state is conserved by using that massive function. And so this is the numerics. So we have this numerical characterization in this way. But this is another problem. So previously we consider energy constraint on the square of number, but now I want to consider without square only one this one, because in the bosonic system energy is given as this one, not n square. So then we want to consider energy constraint. In that case, we have a different solution. This is quite strange. So we consider minimum value, minimum error under this another energy constraint. So then we have a slightly different one. For example, if input state can be described by using this L2 function F, so in that case, energy can be described by in that way. So then if we R is very large, this one behaves in this way. So of course, if we impose some boundary condition F0 equal to 0, so then what happens? We have a much better relation. So we impose this boundary condition. Then this minimum value can be solved by in this way. But this minimization is not so easy. So somehow very complicated. Yeah, of course, I forget this. We need the limit. If energy equal very large, go to infinity, this quantity equal to this one. And this one is achieved somehow Heisenberg scale. But that problem is different from previous one, because previous one we have a square inside of here, but now we have this like outside of the square. So this minimization is quite difficult. But this kind of suboptimal input state achieving the Heisenberg scaling can be realized by two-mode squeezed vacuum state. This is the real. This is my recent result. So that in the case of estimation of SU2, the problem is more complicated. So we consider this energy Hamiltonian. This is corresponding to that kind of this energy corresponds to Casimir operator. This is Casimir operator. And this is same as previous error function. So in that case, this is this way. So then the minimization problem can be solved by using this previous one. So then optimal input is come from the SU2, that bunch function. Then we have this asymptotic behavior. So then we have this graph. Similarly, we have an estimation of SO3. In the case of SO3, similarly, we define this one. And we consider this problem, but this one is have two case. One case is representation case. Another one is project representation case. The support is we have two kind of support. This support anti-periodic part and periodic case. So this is integer case and half integer support. So then we have two different solutions. So these two solutions can be solved in the following way. Integer case solved by this one, and half integer case is solved by this one. But both cases similar graph. One is this one is projected graph. Sorry, this one is projected graph, and this thing normal one is non-projected. This guy, right? This guy is a projected case, a non-projected case. This is the usual representation, and this is the projected case. And also we can consider non-compact representation group. So we want to consider Heisenberg representation. So while Heisenberg case, we have this Fourier transform, and we have this one. Then under this energy constraint, we have this one. So how to derive the minimum one? So we have a Fourier transform, and then we need the minimum under this condition. So the problem is slightly complicated, but the input state is converted by this way. Then under the suitable coordinate change, this means our problem is converted to this one. So only minimization this one under this condition. Then we have a similar minimum value. But now we consider some n-copy settings, or somehow we consider that's what this unitary is previously we consider one big unitary. So we have a parallel action, and we have a one big unitary U tensor N case in some case. So however, sometimes we can consider slightly different situation. This is only the one unitary. For example, this is SU2, and one cubic system. This is one cubic system, and we input some internal state in this. So we repeat this, and after that we apply maximum likelihood estimate. So fortunately, even in this method, we can achieve the optimal performance. So this means that asymptotically, we can achieve this one. So in this sense, we don't need to consider entangled input. This is slightly surprising. So then we don't need to that complicated system. It is enough to repeat this system. This case is very easily implemented. So and also we have a similar one in the case of SO2 and SO3. So this discussion means that when we consider energy constraint, entangled inputs and entangled input and measurement with entangled basis do not enhance the quality of estimation. Previously, we optimized a very big system, and we discussed the asymptotic behavior in the kind of complicated system, big one system. But in practice, it is very difficult to prepare optimum input on the very big system, n-tensor product system. In the practice, it is we can only easily prepare only one copy system. So each one copy system, we can input some optimum system, optimum input, and we take measurement only on the one copy system. And after that, we obtain the data, and after that, we apply maximum likelihood. So that method achieves the optimal performance with that kind of energy constraint. So in this sense, that kind of entangled input and entangled measurement across on the very big system is not needed. Now, finally, I want to move to the answer-tree relation. So answer-tree relation is always we consider on the some real number, but now we want to consider answer-tree relation on the S1 unit circle. So on the unit circle, you can define the L2 function. So in that case, we want to discuss the answer-tree relation on the this function between the yes function. In this case, depending on the input state phi, of course we can define uncertainty of the position. Uncertainty position can be described by this one. So somehow cosine part and sine part. We can consider square variance on the cosine part and the sine part. So real x coordinate and y coordinate. So then we can discuss this one, and also we can define the momentum operator on that unit circle. So we impose some constraint for the momentum operator, square or momentum operator, variance of momentum operator. Under this condition, we can minimize this. That solution is completely same as the previous problem. Then we have this minimization. So by using a massive function, we can solve this kind of uncertainty relation. Similarly, we can consider uncertainty relation on the S3 three-dimensional surface. This one contains the four-dimensional linear space. So, but fortunately, this S3 is isometric to the SU2. So then we can employ the method on SU2. So we consider this kind of one-to-one correspondence between the SU2 and the three-dimensional sphere. So in that case, we can define uncertainty on the position for the four coordinate. And also we can define this one P. P is momentum. Momentum operator is defined by using this derivative. So by using this derivative, we can define this sum of the uncertainty of the momentum. So we consider trade-off between the uncertainty position and uncertainty momentum. So this is can be solved in this way by using a complete same method. Then we have this solution. So this is a conversion uncertainty between the worst case and this one. So yes, so we can also consider different kind of uncertainty. So previously we consider average of position uncertainty, but sometimes we can consider this kind of maximum phi. So we consider this maximum uncertainty, and we minimize this uncertainty momentum under this condition. So then this one can be solved by in this way. So here we need to consider how to say this minimization. So and also similarly we consider similar uncertainty relation on the range of the position momentum, and this is position. So then we have this solution. So I want to skip this one. So then this is the conclusion. We have proposed a method with inverse Fourier transform as a unified approach for the estimation of group action. Using this method, we have derived the optimum estimator with energy conservation in the several groups. We have shown that the entanglement of input and output cannot improve under the energy constraint. We have applied it to the uncertainty equation. Thank you very much. Thanks.
Thank you very much. Any questions?
Can I ask one?
Sure, sure.
Thank you very much. Very interesting talk, very powerful result. I wanted to ask you if you could give some intuition why imposing an energy constraint makes entangled states and entangled measurements useless, basically. What is the point of having a energy constraint? Could you imagine some other constraint different from energy constraint that still gives you product state and product measurement as optimal?
Yes, this is somehow complicated issue because I don't have enough intuition because I only calculate the Fisher information on that situation. So we calculate the Fisher information, then we have that result. But this result only with first type in the case of U1. U1. This is a SU2 case. Yes, this is the U1 case. Yes. So U1 case, I explained two problem settings. One problem setting is square energy, and the second problem setting only the number operator energy. That result only holds with this square energy. If we consider square energy, there is no improvement. But if you consider this energy, I don't have that discussion. Maybe there is some improvement. So if we make out some one copy case, maybe.
I see. I see. So it could be a kind of coincidence.
Maybe, but square is somehow very, how to say, very nice form with this kind of that addition.
Kind of metric.
Matrix. So then we have that equality condition. But if we consider that energy conservation, maybe that does not hold.
I see.
Of course, physically this is very natural, but mathematically, maybe that square is more natural mathematically. But of course, this is not physical.
I see. I see. Thank you very much. Very interesting.
Any other questions? So I just have a quick question. I'm not very familiar with that theory. So I would like, could you explain a little bit the term uncertainty relation? So why do you call your results uncertainty relations?
Because, for example, in that case, in the case of Robertson case, so we consider uncertainty of this, and this is somehow variance of the Q. Usually, in the case of R, we consider variance of Q and variance P.
Okay.
But now we have U1. So U1 is considered S1. S1 can be considered as a subset of R2. So then we define uncertainty in this way. This is variance of cosine Q and variance of sine Q.
Okay, so you look at the relation between the variance of the two things. Yeah, okay. Okay, thank you. Any questions? Any other questions? So if not, I think maybe we can stop here just at the right timing. So thank you again, Professor Hayashi. And now we have the break, the lunch break, and we will start again at 2 p.m. in China and 3 p.m. in Japan.
I will be chairing that session, right?
Yes, yes.
So what time shall I connect? Like 10 minutes prior is enough?
I think so.
Okay. See you. Thank you.